Hello everybody, this is Nick, and today we're going to talk about link budgets. And I've done several videos in the past and I put them on YouTube about link budgets. Today we're going to talk about kind of a special link budget. This is one on satellite going out to GTO. So typically the way I do link budgets is I start with a spreadsheet. And on the left side, for example, column C, I put the elements or the parameters of some of the things that are in a link budget, for example, like the frequency and the bandwidth. And some of these devices or things have values attached to them, and I put the values in. And then, of course, some of these parameters require calculations. So in the column E, I put the results of the mathematical calculations, and in F, I try to put where the sources came from or the formula. So let's get started. So one of the first things you got to choose about designing link budgets is frequency. And from experience on a 1U CubeSat, a good starting place is 0.145 gigahertz. The next thing you got to choose is the data rate. And from experience in the past, 1200 baud is a pretty good place to start with. And when you choose 1200 baud, you also have to choose the modulation scheme. And from experience, we will start this calculation using frequency shift key. Having said that, and knowledge of a little bit of knowledge of Shannon, it takes about 3000 hertz of bandwidth to stick 1200 baud into that. So we'll start with the bandwidth at 3000 hertz. Now, in all satellite systems, you got an antenna that's pointing up in the air, and our satellite will probably traverse pretty close from horizon to horizon, and you got to pick an elevation which to start your calculations. And again, from experience, we'll start it at 30 degrees above the horizon. Now, when you have an antenna that's rested on 145 megahertz, pointing at 30 degrees, it's from experience that the noise temperature on that antenna is about 1000 degrees. That's made up of roughly 2 or 3 components. The major component is the surrounding ambient noise. At this frequency, there's a lot of devices out there that generate noise. And the second component is the black galactic background. From experience, a pretty good starting point is 1000 degrees Kelvin. So now, one of the major components that you have to think about is at the ground you want to put a low noise amplifier. And those amplifiers come in lots of flavors. And the basic description on a low noise amplifier is its noise figure. You can Google and learn about noise figures and amplifiers. And the more expensive amplifiers can, at these frequencies that are uncooled, can come in with noise figures of 1/4 dB. But actually, 1 dB is a pretty good design, and at these frequencies and these temperatures, 1 dB is sufficient. So once you have the noise figure of your amplifier, we choose to convert noise into its equivalent temperature. A guy by the name of Planck, a century or two ago, said that all bodies radiate wideband noise, and that noise in watts is equal to the Boltzmann constant times the temperature times the bandwidth. We'll talk more about that later. Now, once you know the noise coming off the antenna and you know the noise in the amplifier, we generate a term called the temperature system temperature, and that's simply the sum of all the noise sources. In this case, it turns out that our system temperature in this link budget is 1075 degrees Kelvin. Now, one of the givens in this thing is that this thing is going out to GTO, so the distance between the transmit antenna and the receive antenna is in the order of 22,000 miles. NASA, since they list the orbit, puts it in orbit, that's a fixed known quantity. So now, engineers, comes the hard work. So you have to decide how much power you're going to allocate for the transmitter on the orbit. It turns out, from again experience, 1 watt is achievable. And because we're satellite engineers, we tend to express most of our measurements in dBm. And you again, how to get there is beyond the scope of this video. Simple logarithmic math. So let's start out with 1 watt, which is equivalent to 30 dBm. The next thing you have to design is the antenna on the satellite. It turns out, and I'll try to highlight this as we go, it turns out that if we can produce an antenna on the satellite that essentially puts out radiation in all directions, you describe that antenna having a gain of 0 dB. Tough to do on our satellite, but we've got to plug a number in here, and we choose to plug the gain on the transmit antenna at 0. Now the next major loss we encounter is that this satellite is out 22,000 miles away from our receiver. So as you move further and further away from the transmitter, the received signal decreases. You guys kind of have an anecdotal experience like that. If you have a flashlight and you shine it on an object that's 1 foot away, it's probably pretty bright. If you shine it on an object that's 10 feet away, it gets a little dimmer. And if you shine it on an object that's 1,000 feet away, you know the light is there, but your eyes, it comes in where your eyes can't detect it. Same thing on a satellite. So now, the next major component in the system is the receiver gain, the antenna at the receive site. All right, and by intuition, you think the bigger the antenna, the better it is. Well, that's exactly the case. And from experience and what we have here on campus, the antenna on top of the engineering building has a gain of 14 dB reference to an isotropic source. If you wanted to make that gain higher, you could double the area of that antenna and gain 3 dB. So every time you increase the area, double the area, you increase the gain by 3 dB. So if you when you double it again, you could gain another 3 dB. But now you got a pretty large antenna, and as you add gain, it gets tougher to keep the antenna pointed. But that is something, as engineers, you decide, and you get to choose. So now we have enough information to calculate how much signal that leaves the satellite will appear on the ground. And because we have chosen to put all of our engineering units at decibels, or decibels reference to 1 milliwatt, it's easy to calculate that receive gain. It turns out it's the algebraic sum of the past 4 targets we've talked about, and they're depicted in this spreadsheet, starting with the transmit power, the antenna gain, the free loss space, and the receive gain on the ground. So it turns out that if we choose to let our satellite radiate 1 watt, it will get on the ground at minus 122.7 dBms. That is a fraction of a microwatt, not a very strong signal. So now that we know the signal, the next thing we need to do is to calculate the noise. Well, we know the 2 components of the noise come from the noise coming off the antenna, which we guess to be about 1,000 degrees Kelvin, and the noise generated in amplifiers. So the total noise in the system now is just an algebraic sum of those temperatures. So now that we know the temperature, we need to convert that back into watts. Thanks to Mr. Planck, he has given us a way to do that, and he says if we know the temperature and we know the bandwidth at which we're trying to calculate that noise, then all we have to do to calculate that is to multiply Boltzmann constant times the bandwidth times the temperature, typically known as kBT in our profession. We take the logarithmic version of that. We just simply take 10 times the log, and since we like to reference things in dBm, we divide it by 1 milliwatt. And so now we calculate the noise by this formula right here, and that turns out to be 133 dBm. So now that we know the signal and we know the noise, we can now calculate the signal to noise ratio. And since we're working in dBs, it turns out to be the algebraic sum of the signal minus the noise. That says, doing that calculation, we say that we have 10 dB of signal to noise ratio. Now that we know this number, we've also decided that we're going to use frequency shift modulation, and through Shannon and others, we know that the modem will, if we send the modem 7 dB of signal to noise, that modem will produce a digital stream that only loses 1 bit per every million cent. And that's a design number. If you want to if you have less than 7 dB, the bit error rate, or the errors coming out of that modem, goes up significantly. In fact, at 5 dB of signal noise, you almost have no coherent data coming through that modem. That's another discussion for another day. So, so now if we have 7 dB of required signal noise, but we actually are producing 10, that says that we have 3.8 dB of margin, and that is called link margin. And that's just the algebraic sum of what we have to what we need. Now, this is a simplified link budget. There's lots more things to consider, and just because we have, incidentally, this link margin has to be positive for us to close the link. If it turns out that it's negative, we don't get any data through, and we say the link fails. So don't get excited because we have a little margin. One of the things, the major things that we haven't accounted for is polarization loss. Now, this satellite out there is kind of tumbling in space. The polarization is constantly changing. The polarization, gee, where did my face go? The polarization on the antenna on the ground is fixed, so we have additional losses, and these losses could be significant, in the range of 20 dB. So at certain times, that thing will be misaligned, and we will lose the link. One of the ways we mitigate that is we put a couple of antennas on the satellite, and we actually change the polarization, or the orientation of the polarization. Also, we hadn't accounted for the feed line losses, and again, this is a topic for another day. So guys, here's my thoughts. It's a real quick run through, and I encourage you guys to study this thing and have further conversation with it. So long for now.